Thank you so much for joining in. In this particular session, I'll be talking about optimizing latency for production-grade voice agents. And my name is Akash Hamirasia. I work as an engineer at ElevenLabs, and I mainly work on the creative platform, so technologies like text-to-speech, voice cloning, voice library, voice design, speech-to-text, and so on. I go on Twitter by @BlenderSchool. I post about ElevenLabs, about things that I'm working on, or any side project that has caught my eye. I also love sharing technical talks, writing technical blogs. You can check out some of my past content on my personal website, akashhamirvasia.com. So in this talk, I won't be just pitching about ElevenLabs. I'm not a salesperson. I'm an engineer. So I want to show you some use cases and some problems that we were able to solve in our voice AI platform that you might be able to incorporate in your own agent solutions that you're building. So this is a complete suite of what ElevenLabs is. You might know of ElevenLabs as the text-to-speech platform. That is one part of our product. We allow you to generate very realistic sounding speech from text with any voice and any other language. Currently, we support 12 Indian languages and over 80 global languages. Apart from this, we also have voice cloning. So if you want to clone your own voice and produce content in that, you can do that on our platform. If you want to use voices from other voice actors, we have a voice library where people have cloned their voice, and they can also earn commissions when you use their voice. We also have a dubbing product. We were fortunate enough to partner with Lex Friedman and Narendra Modi for the podcast that they had produced, and we were the official dubbing partners where we were able to localize their content in 29 different languages with our AI dubbing. There's also music. You can generate music from text prompts, sound effects. We also have a consumer app for reading content on the go, and also speech to text. So this is opposite of text to speech, where you can bring in any audio and we can transcribe it into text, separate the speakers, who said what, and so on. The biggest piece that we will talk about in this session is the agents platform. This platform allows you to build smart AI agents that can speak with low latency, full configurability, and seamless scalability on the web, mobile, or telephony in just minutes. Now, as developers, all of the features of ElevenLabs is also available as APIs. So there is text-to-speech API, there is speech-to-text API, the voice changer API, and the entire agents platform to build your own AI agents is exposed as an API so that you can build your own products on top of it. Let me give you a quick walkthrough of what our text-to-speech is like. All right. So this is our text-to-speech product. I've selected our latest 11v3 model, which has expressive audio tags, and I can define my speech in this way. So I can start by saying laughs, and the produced audio will start with laughing sound, and so on. So let's generate speech and listen to what it can produce.
All right. Guys, seriously. Can you believe just how realistic this sounds now? I mean, oh my God. It's so good. Like, you could never do this with the old model.
So this is 11v3. I demoed it with English, but you can also use Hindi, Kannada, any other supported language. And there's also thousands of different voices that you can use to generate content. In the interest of time, maybe after the talk. Cool. So how many of you are familiar with voice AI agents? Okay, a lot of you, which is good. I'll give you a quick overview of how a very basic architecture of a voice AI agent system looks like. So voice AI involves three important pieces. There is speech to text to understand what the user is speaking. You transcribe it, you convert it into text, and then you send it to this intelligence layer, which right now is an LLM. So it understands the user's query, produces an output. In some cases, you might have your RAG system to provide extra knowledge to the agent. You might have tools connected which can execute certain tasks in other systems. And once the response is ready, it is converted back to speech and is relayed back to the user. Now, things start to get quickly really complex when you introduce in these things called voice activity. You have to detect when the user is speaking, the agent should not speak or interrupt the user. So this is at a high level how it looks like. Now, we are very bullish on voice agents, and we are dogfooding our own product. And you will see on our documentation site, there is a widget at the bottom, which you can start a conversation with, and it'll guide you to any part of the ElevenLabs docs in minutes. You can ask, hey, how do I do text-to-speech? It'll take you to the text-to-speech page at the relevant section so that you can get the idea of what you want. It's also there in our own product. This one is much more smarter, so it can also click on elements on the page. It can run certain actions. It's not just a conversation, hello, hi kind of thing. It does actions on the page as well. I'll give you a quick demo of a very interesting agent someone from our team actually created. So this one is in Hindi, which is very interesting. Let's start.
नमस्ते नमस्ते, मैं नीरज हूं, आपका थोड़ा ज़्यादा ही इमोशनल, थोड़ा ज़्यादा ही मजाकिया साइंस टीचर। अरे बताइए, आज किस फॉर्मूले की धुनाई करें? न्यूटन, इलेक्ट्रॉन कि ब्लैक होल? सब तैयार है, बस आप बोलिए।
ग्रेविटी के बारे में बताओ।
अरे वाह, ग्रेविटी, ये तो मेरा पसंदीदा टॉपिक है। मतलब ग्रेविटी ना, वो जादुई शक्ति है जो हमें धरती से चिपकाए रखती है। सोचिए, अगर ये ना होती तो हम सब हवा में उड़ रहे होते, जैसे कोई गुब्बारा। है ना कमाल की बात?
नहीं, ग्रेविटी नहीं होता।
क्या? ग्रेविटी नहीं होता? अरे रे रे, ऐसा कैसे हो सकता है? मतलब अगर ग्रेविटी नहीं होती तो हम सब अभी तक अंतरिक्ष में तैर रहे होते, जैसे कोई मछली पानी में। आप शायद कुछ और कहना चाह रहे हैं, है ना? मुझे थोड़ा और समझाइए, मैं थोड़ा सा कंफ्यूज हो गया।
So this is a very basic demo of a science teacher, very expressive one using our agents platform. You can really make it really complex quickly. So this is a very simple AI assistant that I built, which connects with my Google Calendar. It uses MCP servers to connect with Google Calendar, Gmail, and it can run actions on my account as an agent. So I can ask it to check my calendar, schedule meetings, reply to emails. There is a workshop that I have done in the past that you can check out. Coming back, so we have gone through this. Cool. So you can also use the entire agents platform via API. This is how easy it is to actually create your first agent. You need to define your system prompt, the settings of the voice that you want to use, the model, the first message, and your agent is ready. Slowly, you can modify it, make it more complex, add tool calling, and other settings as you go ahead. Now, let's take a look at an architecture of a voice agent system and try to understand where are the latencies that creep in when you're building a system like this. The first part is ASR, which is speech recognition, something that takes in input speech from the user and converts it to text. Now, this part mostly runs in background, and the measurement for the latency of this is the time between the end of the speech and end of text generation. So in the previous slide, ASR is running while the user is speaking, but once the speech is stopped, the extra time it took to actually complete recognition is the extra latency that we have here. So short and long speaking intervals actually can incur the same ASR latency. It does not make a huge difference if you have long queries by the user or short. It's just the extra delay that gets added. Depending on where you have this ASR model deployed, you might not have any latency at all. So if you're using on-device transcription, like Chromium has a model, I'm sure even Android has one, you won't add any network latency. The open source model Whisper, if you're using that, it adds a standard 300 milliseconds plus of latency. And our own implementation of ASR, which is integrated in our platform, adds less than 100 milliseconds of latency. So after ASR, the next piece comes in is the voice activity detection system. This detects when the user is actually speaking and when the user is silent. So to make this work, there are a complex set of rules. Essentially detects when the user is silent, so that once the user is silent, the agent starts responding. Sometimes the user might say stop words like, but that time you don't want the agent to pause because the user hasn't given a long enough query. So there are complex set of rules. It adds a little bit of latency, but honestly, this latency is actually fine because if you're building a realistic voice AI agent system, you want a little delay between the response from the agent and input from the user. Because as humans, we don't talk continuously one after the other. We take some time, think, and then respond. So some delay over here is not really bad. Now, the next piece, this is really important and plays a key role in the final latency of your system, which is the LLM piece. LLM is the brain of your AI agent, and depending on which agent or which LLM you use, it will affect the latency in that way. So the measurement for LLM latency is the time to first response. After the first token is sent by the LLM, the further tokens are really fast. It's much faster than how humans can actually generate speech. So just measure the first time to token. And if you are using some of the flash models like Gemini 2.5 Flashlight, we have observed it gives around 400 milliseconds of latency. 4.1 nano from OpenAI, this is 500. And some lighter weight models like Qwen 3 gives as low as 173 milliseconds of latency, which is really nice. This thing keeps changing depending on the provider load and various other factors. But on ElevenLabs, we have this section where we show the latencies of each model. And this is measured across the last 7 days. So you can see which model is actually getting slower due to any reason that might be there on the provider end. The other big factor here is the Flash and thinking models. In most cases, you might want to use Flash because that's the fastest model. It gives outputs really quickly. But then it's also not very accurate. If you're building an intelligent system, you need a thinking model which can actually think and respond to the user's query. So Gemini 3 Pro, this model takes around 4 seconds in latency, and GPT 5.1 also is above 1 second. It's quite large, not really good for real-time voice AI agents. So a solution for this is to actually use a multi-agent architecture. So you will have a simple LLM, a lightweight LLM at the top, which can handle, let's say, 80% of the user's query. And when you have a more complex use case by the user, let's say in this example, the user is asking a math problem, this Flash model decides that, okay, I can't handle this. I should relay it to this Gemini 3 Pro model. So that way, most of my use cases are handled by a lightweight model. It doesn't cost a lot as well. Delays are also low. But if there are complex use cases, that is when the Pro thinking model kicks in. This is very easy to do on our platform. You can define these workflows and conditions as to when the agents should actually switch. Another alternative to improving LLM latency is to use a custom LLM. Depending on whether it's possible in your organization, you can actually fine-tune an LLM with your own knowledge base and cut down the size of the LLM and reduce the latency over there. If you're using a custom LLM on ElevenLabs, you have to use the OpenAI Responses API spec, and you can define the custom LLM in code, and it'll call your LLM with the context. Now, the next piece after LLM is text-to-speech. So once the output is generated, this is sent to text-to-speech model to actually create the audio. To measure the latency over here, it's the time to first audio, the time it takes from the input to the first audio that is received. That is the longest time. After that, it's really fast. It's much faster than what humans are able to speak at. Now, early TTS models used to be quite slow. It used to take as long as 2 to 3 seconds. Our turbo models that we have on our platform is able to generate speech with just 300 milliseconds of latency. Flash is a new architecture that we had launched a while back, and this has a model time of 75 milliseconds and end-to-end latency of around 135 milliseconds, which is the time to first byte of audio latency. And this is all while supporting multiple languages. The V3 model, which I showed at the start, this is also soon coming on the agents platform, which will allow you to have these expressive laughs, sounds, whispers in your conversation. And I can't say how fast it will be right now, but it is something that will enable more expressiveness in your voice agents. Now, these are simple high-level latencies that we have identified from building agents which cover almost a lot of different use cases. But there are other latencies as well. For example, so another important latency to consider is network. When you have systems and these components at various different provider levels, they all add a significant amount of network latency. So ASR is at one place, voice activity detection is at another place. LLM is, let's say, your OpenAI, Gemini, TTS is another provider. So all of these hops that you have between multiple services, they add a lot of different latencies as well. Now, luckily for us, if you're using our orchestration platform, which is the ElevenLabs agents platform, we have our own ASR and text-to-speech. So you essentially save on 2 network hops because it's within the same system. And we only have the latencies at the user level, which is at the browser, and the LLM level, which is to the LLM provider itself. So network latency associated with sending data. For getting 0 network latency, ideally all components should be co-located. There are also real-time models that do not have any network latency because everything is happening in one model. But yeah, for the time being, at least in our system, how we have implemented it, you can actually save 2 server calls because of our own solution for TTS and ASR. The other important bit that adds a lot of latency is function calling. If you're building a smart agent, you might have API calls or tools that you might add to this agent. And depending on how many tools that you have, each API call could add significant amount of latency. So function calling requires additional API calls. It can significantly increase latencies due to complexity of the system. Imagine a use case of ordering a pizza. There are so many different steps, and you might have one API call for each and everything, which returns back the data, and then it just adds a lot of different latencies and makes the process really slow. Now, the solution to actually solve this is to use an architecture like this, where the function calling happens in the background, and your LLM calls run asynchronously. So as the function call is triggered, the LLM responds by saying, okay, I'm taking a look at it. And that way the user is engaged. And the function calling is still running. The user can still chat with the agent, and once the response comes in, the user knows, okay, this response is processed. So the user is not blocked and kept waiting for the response of the API. So this is what we call async processing of functions. You can prompt the LLM to respond to the user before the function call is finished. It keeps the user engaged. And on our platform, this is accomplished by leveraging webhooks. So our platform would call your APIs in the background, and we don't block the user to wait on the response of these API calls. This is how it looks like on our platform. So similar to how you define an API, you would provide your URL, the API call, any headers that you might have. All of these can be programmatically sent as well, any authorization codes. There is MCP support as well, so you could bring in your existing MCP servers, and it'll all be optimized to run in the background. Now, monitoring is a very important part to actually measuring how fast your system is. So on our platform, you will see monitoring at every step, and you can see at text-to-speech level how long did it take. For ASR, how long did it take, and so on. So you can observe which part is actually slow. In most cases, it will be LLMs or function calls, and then you can go about optimizing those. Additionally, you can also observe the overall recording, the duration, the cost that you incurred with this conversation, and other details. Now, finally, there is this very niche use case, but it is actually becoming very relevant in India, which is telephony. So imagine an AI agent which can call the user on their phone, and the conversation happens on the device itself. The user does not have to download an app, open links, or browsers. Now, this is a very legacy system in a way, and it has its own latencies, so you have to account in this particular part as well. And what we have observed is any telephony system will incur an additional 200 milliseconds of latency if it's contained in the same region. So if it's within India, it's 200 milliseconds. But if you're using, let's say, services like Twilio or any service that makes global calls, then that could add 500 milliseconds of latency, which is quite significant. So something to consider if you are building telephony in your AI agents as well. Finally, the last piece I would like to talk about is touching on RAG, essentially providing knowledge to your agents. And it can be done in 2 ways. First is, of course, directly include it in your system prompt. So if you have, let's say, some document, paste the context of that document in the system prompt. The other option is using a RAG pipeline. Now, I don't know why everyone loves RAG a lot, Maybe it's because it sounds cool and I'm an AI engineer. But honestly, RAG is not always the solution. It adds extra latency without you realizing it. And as long as you can fit your knowledge in the system prompt, it's fine. You should go about doing it. It might cost a little bit more, but you don't have to deal with the headache of maintaining vector databases, network latency, and then observability of those extra systems. So a very simple thought process is if you have a huge collection of documents, in this case, it totals to 2.6 million tokens, that won't fit in a context window of a particular model. So in that case, it makes sense to use RAGs. But if you have, let's say, a 4-page policy, 3,000 tokens, it's fine to just include it in the context. There are a lot of different strategies for including knowledge in your systems. I'll just quickly cover a few of these here. Single agent knowledge base is something we are familiar with. You either have RAGs or you paste it inside the context. The multi-agent knowledge segregation is an interesting one. This is similar to the workflows piece where the first agent figures out what the query is about and then redirects the request to the next agent which has the knowledge about that context. So that way your primary agent does not have thousands of documents to deal with. It just knows that, okay, for, let's say, ticket processing, it goes to this agent. For refund processing, it's this agent. And then the respective agents have their own knowledge included. The third strategy that we have seen is knowledge base for discovery and tools for data. So let's say if a user asks, hey, can you tell me more about the Pro plan? Now, your Pro plan might be mapped to some ID on the database. So your knowledge base could say, if the user asks about Pro plan, the plan ID is this. And then you can use tool calling to actually get the data from the user's database. So you can do an API call, fetch the data, and then that acts as the knowledge. So you don't need RAG or any sort of vector database here. The fourth strategy is external vector database. It has its place if you have a lot of documents converted to embeddings in Pinecone or any other database, you can integrate it as tool calls. It'll add some latency because it's outside of our system. It's on your system, so the network hop will be there. And if you can use our own RAG solution that we have on our platform, then that latency could also be reduced. The last one is a very interesting one. This is dual brain architecture. So what we have observed is some companies have their own custom LLMs, but they are not very fast. It's fairly slow, but if you want to bring that knowledge into an LLM, you train or fine-tune a custom LLM. It might not be very fast, and then you use the redirection flow where the starting agent is like understanding the user's query, and then if it is something that's related to your context, redirects to your model depending on how loaded it is. Finally, for further reading, if you are interested in more about latency performance improvements, you can check out this article, which we have written, how we engineered RAG to be 50% faster. You can scan the QR code, it'll take you to our blog. And finally, I just want to thank all the companies that we have been able to partner in India. This has allowed us to bring our AI voice advancements to the apps that you know and love. So you might have interacted with one of our voice AI agents if you have used any of these platforms in the past. Like I mentioned, we support 12 Indian languages and accents, and there is India data residency available as well. So that should also lower your latency. There are GDPR compliances, HIPAA compliances that we comply with. And we also have our own local team. We have a booth over here outside, and there's 2 of us right now, but in India, there's 15 of us with local support for any enterprise and SLAs. Finally, if you're building a startup and you are using ElevenLabs, you can apply for our grant. It gives you 12 months free access to our entire platform. 33 million characters, which is equal to 680 hours of conversational AI content, and the scale plan, which allows you to create professional voice clones and deal with extra concurrency limits. So you can apply for it at elevenlabs.io/startupgrants. With that, I come to the end of this talk. Thank you so much for listening. I would love to continue the conversation further outside the stage. Thank you so much.